Hello and welcome to lecture number 2 in the course Advanced Robotics Applications. In the last lecture, we looked at Introduction to Robotics and we saw that robotics is a part of automation. And we have seen that automation has progressed over the last thousands of years from very simple things like tools to the invention of the computer, after which we had NC, CNC, DNC, SIM, and robotics. And in terms of robotics also, we have seen that robotics has progressed in terms of having greater interaction with the environment, in terms of having better sensors, actuators, and in terms of controllers and algorithms. So today we'll progress from where we left off in the last class. Today I'll start off by giving a very brief introduction on AI. So we are in the fourth generation or future robotics, where one of the importance is in terms of the algorithms, and the other is in terms of in having smart actuators, sensors, controllers, in that order. Now, after that, we'll move on to looking at robot joints, and by having different kind of joints, you can make different kind of robots, and then these robots can move around in space, and that area where they move around is called the work volume. So today we'll look at these two concepts. Now, before I proceed, I'd like to say that this is a very brief introduction on AI. AI is a subject in itself, and which cannot be covered in a few hours and in a few lectures. So this is very, very brief, just to show the application of AI in robotics. And when we say AI in robotics, so we say intelligent robot, what do we actually mean? Okay, let's continue from where we left in the last class. And after the third generation of robotics, we have the fourth generation, where basically we say enter AI, or where AI has entered and we are having smart algorithms. And today we tend to say that a robot is intelligent, or we talk about intelligent machines, intelligent algorithms. Now, when we say intelligent, what do we actually mean? So this word intelligence, how do we define it? Or can we define it? That's a more important question, interesting question. Now, there has been a lot of impact of AI, and there are a lot of movies around. You might be familiar with some of the movies. They are very, very interesting and important movies, in the sense that they talk about what AI is in the area of robotics and what the future is likely to be. May not be in 100 years, maybe 200 years, maybe 200 years after from now, it will be something like this. Okay, so a lot of this is based on science, and these are movies. Of course, movies may come true at some point of time. Now, coming to the point of intelligence, or if we are directly looking at what is AI, then we can say that in terms of AI, we basically talk about systems that think like humans. So systems that think like humans and systems that act like humans. Okay, so when I said in today's class, we talked about intelligence. So this business of intelligence always has a human attribute. Okay, so there is a human attribute in here. So there is a human attribute. So whenever we say, what I mean by this is, whenever we talk about intelligence, we try to relate it to a human or human attribute of intelligence. What do you mean by intelligence? If I say, are you intelligent, or he's more intelligent than him, what does that mean? So there is this human attribute or connotation or attachment which automatically comes when we talk about the word intelligence. Okay, so in terms of a system, here we are relating ourselves only to robots. Okay, so we might say that robots that can think like humans and robots that can act like humans. Now, what does that mean? Now, that essentially means systems that can think rationally and systems that can act rationally. Okay, so now, if you look at AI, essentially AI is not only one subject, it is an amalgamation of many, many subjects together. And AI has been around for a very, very long time. It's not again like AI was just invented a couple of years back. So something like automation is thousands of years old. So similarly, AI is also thousands of years old. So AI is made up of these subjects, philosophy, okay, right from the term of Aristotle. Okay, where Aristotle asked this question of foundations of learning, rationality, language, then mathematics, then economics, then we have neuroscience, psychology, we have computer science, control theory, linguistics, robotics. So all these basically make up AI, or different aspects of AI. And what do they have in common? This business of having some attribute of human intelligence, okay, or relating it to human intelligence in some way. Okay, so we are basically looking at here the part of robotics, and we are saying that robots that can think like humans and that can act like humans. Okay, so when we say AI, so what is AI? So it is the science and engineering of making intelligent machines. Okay, especially intelligent computer programs. So we are continuously repeating this word intelligence. So if you were to ask that, yes, we understand that, but what is intelligence? So intelligence is the computational part of the ability to achieve goals in the real world. Okay. So in the case of robotics, we can say a robot which can decide or plan by itself, okay, without human intervention. We can say it has some kind of intelligence. Okay. Now, is there a solid definition of intelligence? Apart from that, or just relating it to human being, is there something which is a solid definition of intelligence that does not depend on relating it to a human? Well, not as yet. Whenever we talk of intelligence today in any form, we are always relating it to a human only. Okay. Now, the essential problem is that, so we cannot characterize in general what kinds of computational procedures we want to call intelligent. That is something that we still don't understand. We understand some of the mechanism of intelligence and not others. Okay. For example, human beings behave in a particular way, or speak in a particular way, and respond to questions in a particular way. Okay. Now, some of it we can say is intelligent, others we don't understand. Okay. So there is no formal definition of intelligence as of today which is not related to a human. Okay. Now, very interestingly, in terms of in the concept of robotics, the English mathematician Alan Turing came up with this Turing test. Okay, to check machines and humans apart. Now, what Alan Turing said is, if you can make a machine or algorithm intelligent, how do you prove that it is intelligent? Okay. So the question is, if I make a robot or you make a robot, we'll be doing experiments in robotics, and if I say this robot is intelligent, okay, how do you prove it or how do you disprove it? Okay. So Alan Turing essentially proposed this, what he calls the Turing test, to check machines and humans apart. Okay. And his his test was very simple. How to check if a robot is intelligent, okay, or a computer program is intelligent. And he said that if the machine or the computer program can fool a human into thinking that it's a human, then probably it has passed the test. Okay, and this is what the Turing test is something like, and it was designed this way. So suppose there is a computer program or a robot sitting in one room, and there is a human who is sitting in the other room. Okay, and they cannot see each other, and they are completely enclosed in the room. And on the outside, there is what we call an interrogator, or another person who's sitting there is called interrogator. Okay, so there is an interrogator there who is basically going to check if the human and the robot can fool this person. Okay, now the function of the robot is to fool the person into believing that it is a human. Okay, so if the robot can fool a human into thinking that it's a human, then it has passed the test. That is what the test is, which basically means that it is intelligent. Okay, now this can be a robot, it can be a program. Okay, now this person can communicate, who is sitting outside, can communicate with the robot and can communicate with the human, not only by means of a typewriter, only by typing. Okay, and not by speaking or by seeing. So the person can type a question and pass it here and pass it here. The human and the robot answers the question and passes it back to the interrogator or the human sitting outside. Okay. Now, if the robot can fool this person into believing that it is a human, then it has passed the test. Okay, and that is basically the Turing test, and it is basically to check machines and humans apart. Now, this is it may seem very simple, but it has a lot of other subclause, and but we'll not get into that at the moment. But essentially, this is important in the case of robots, because if we say a robot is intelligent, how do you know it's intelligent? If a computer program is intelligent, how do you know it's intelligent? One way could be to check if it can fool you into believing that it's a human. For example, when you're chatting, or you go to this help in various, I'm sure you would have gone to various helps. For example, during banking, or when you're chatting with something online. Okay, how do you know that it's a computer, or it's a computer program, or it's a human? Okay, if it's a program and the computer program can fool you into believing that it is actually a human being, then it has passed the test. Now, I'm sure that you would have had the experience of this, of chatting online or by asking questions online. You get immediate answers. Okay, but after some time, the answers stop. Okay, indicating that there is a limit to what the program can answer. After that, it just passes you to a human operator. Okay, this you would have experienced, and this is essentially what is called the Turing test. Okay, so if somebody were to make an intelligent robot and say it is intelligent, how would you check it? You can check it by examining if it can fool you into believing that if it's a human. Now, this is also something which we are subjected to, which is called the reverse Turing test, and this is called the CAPTCHA, which again you are subjected to many times in a day. Whenever you log into any website like banking website or ticket reservation website, they check, okay, if you are a human or you're a machine which is doing that. And that is basically what is called a CAPTCHA. So a CAPTCHA is essentially completely automated public Turing test. So this is a Turing test to tell computers and humans apart. So it's not only that we are trying to check if a machine is intelligent or a human, but this is a machine which is checking if you are a human. Okay, so these are what are CAPTCHAs you must have seen. So for example, you can see this and it says that please enter what you see here. Okay. So basically a human being will say that it is tame, T-A-M-E, whereas if it's a computer which is progressing, it will tend to confuse this also and say that's an S there. So immediately you'll get confused. Okay. Whereas a human will not get confused. This is basically the difference in intelligence between a machine and a human. Okay. We are not getting into that in detail, but we'll leave it there. This is very interesting. As of today, we have very complex computer programs which can behave like humans, but at some point you can make out that it's not a human, it's a computer program. Okay, and the day a computer program can actually fool humans, it can be called intelligent. Okay, so what we see here in this very brief, what I was trying to explain, is that the business of intelligence for a machine is always in relation to human intelligence. Okay, and as of today, we don't have machines which can actually which we can say are as intelligent as humans, but maybe we'll have it someday. But this is that essential test that. Now, apart from that, we also have autonomous cars, which tend to have some amount of intelligence, which means that they can behave like humans, okay, in terms of driving or in taking decisions. Okay, so they are intelligent in some form, or they have some amount of intelligence. Then we have robots which can move around autonomously like humans. Okay, so this is the big dog. So the big dog is a quadruped robot that can walk in any kind of terrain. It can carry heavy weight. It is dynamically balanced. It can find its own way. It's like a human. So it has some amount of intelligence for path planning and autonomous navigation. So this was an example of a big dog, a quadruped robot made by Boston Dynamics. Now we also have a more advanced biped. So this is a biped robot which can walk around and find its own way around. For example, it doesn't hit obstacles, it can find its own path. Walking in difficult terrain like snow, even human beings will find it difficult to walk in this kind of terrain. So this has some amount of intelligence. But is it as good as a human? No, probably not. So you always see that intelligence tends to get related to some attribute of humans. That's where we are at the moment. Okay, now with this brief discussion on intelligence, let's not go any more into that direction. I hope you get some idea of this business of intelligence, and when we say a robot is intelligent, what do we mean? Now let's move on to a little bit more serious talk on robot joints and work volume. Now most of our discussion is related to serial arms, serial robotic arms. Now a serial robotic arm is one in which the end effector or the end of the robot is free. It's like our hands. So our arm is fixed onto the shoulder and my hands are free. So you can move your hands in space and the hand is free to move around. Okay, only the base of the hand is fixed onto the shoulder. So in this robot, the base is fixed. It doesn't move. So that's a fixed base. Whereas this is the end effector. This is called the end effector. Okay, in this particular case, it can also be called the gripper. Okay, so the gripper or the end effector is the one that moves around in space. Okay, and this is called a serial arm. Now you can have two grippers holding an object. So this is an object which is held by two grippers. This is one here. So this is one robot, serial arm. There's another serial arm. Okay, both of them are fixed here and here. But on the free end also, they are holding an object together. So they are constrained. So this is something like a serial arm. This is something like a parallel arm. So we have a serial arm and we can have a parallel arm. Okay, serial arm and parallel arm. Parallel arm is one in which it is constrained, the end is constrained, with respect to something, like in this case it is holding an object and it is constrained. This is a parallel arm. Okay, so what we see is that these are this is a serial arm robot, and these are what we call joints. Okay, and these are links. So we have links, we have joints, and the links are connected by joints, and by this we have we can define a robotic arm mechanism. Okay, in this particular case, it's a serial arm. In the serial arm, this is called the end effector, and the end effector may be a gripper or it may also be a tool. Okay, for example, if it's doing spot welding or spray painting, then it can be called a tool. Okay. Now, so there are different kinds of joints which connect links. Let's look at some of the joints as we proceed. Now, before we proceed onto the joints, let's talk about degree of freedom of a system. So these are terms that we'll be using as we go along. So let's define them here. Now, degree of freedom of a rigid body, when we say a freely floating rigid body in space, for example here. So you can think about a cube or a cuboid which is freely floating in space. Okay, so it is not connected to anything. So it's freely floating. Maybe there is no gravity in there. Now, what we do is we define an axis here. Let me call x, y, and z axis. So this is my x axis, y axis, and z axis. And this body can translate along the x, y, and z, and it can also rotate about the x, y, and z. Okay, so it has 3 translations, and it has 3 rotations. Okay, so 3 translations and 3 rotations, and hence it has 6 degrees of freedom. So each of this corresponds to 1 degree of freedom. So if it has, if it can move along the x direction, we say that it's 1 degree of freedom. This is 1 degree of freedom here, 1 degree of freedom here, and it can rotate about x, y, and z. It has 3 rotations, which are called x, y, 3 rotations, which make up a total of 6 degrees of freedom. So this freely floating body has 6 degrees of freedom. It has 3 translations and 3 rotations. Okay. Now, with this, let's move on to the concept of joints. Now, the first kind of joint is a prismatic joint. Now, what does the prismatic joint look like? So it's a prismatic joint has a rectangular or a square cross section. So this is a rectangular or a square, and there is a rectangular or a square cross section which is fitted onto it. So this part, which is mounted onto this joint, is also having a rectangular or a square cross section. Okay. Now, as you can see, that this is called the axis of the joint. That is called my axis of the joint. Okay. Now, because this is a rectangle or a square mounted on another rectangle or square, this cannot rotate about that direction. Okay. There is no rotation. It's not possible for this joint to rotate, but it can move up and down. So if I give a force here, it can come down or it can go up. So what we have is a variable distance. So that variable distance is an x. Okay. So this is a variable distance which is called x. Okay. And it can go up and down. And this joint is called the prismatic joint. This is called the axis. Please note, this is called the axis. It has 1 degree of freedom. The variable is the distance variable. So it has a translational distance variable. It has 1 degree of freedom. Okay. So this is called a prismatic joint. In short, it is termed as P. And it has 1 degree of freedom. Now in this one here on the left hand side, the revolute, please note that there is a stopper there, so this cannot come down. Now in this case, this is a cylindrical part which is mounted on the cylindrical rod. Okay, now because this is cylindrical, this can rotate about this joint. Now the axis here is, this is the axis. Now this can rotate like that and like this. Okay, so it can rotate about that axis, but there is a stopper here. Let's call this a stop here. So this cannot come down. Okay, so this is a fixed distance, it cannot come down, but the variable is the variable angle. So if I give a force here, this can rotate about the axis. So it can rotate, but it cannot come down. Okay. Now this has also 1 degree of freedom and is called the revolute joint. In short, it is defined as R, called the revolute joint. Okay. Now, if I remove the stopper, then we get a cylindrical joint. Now in the cylindrical joint, this is a cylindrical part which is mounted on this cylindrical part, and this can go up and down. Okay, this can go up and down, and it can also rotate. Okay, so this is my axis. It can move this part. I mean, this part can go up and down. So there's a variable distance. We can call it x, and it can also rotate about this, so which is theta. So it has 2 degrees of freedom. It has an x and it has a theta. Okay, this one has only 1, which is a theta. The previous one has only an x as the degree of freedom. Okay, so we have a prismatic joint, We have a revolute joint and we have a cylindrical joint. Now this is called a spherical joint. It can also be, it is sometimes also called a ball and socket joint. Okay, this is also sometimes called a universal joint. Okay, so there are different names for this joint. Now it's easy to understand why it is called a ball and socket joint. So this is a ball which is inserted into a socket. So this is my ball and this is a socket or a cup. Okay, so this ball is inserted into that cup, and if I put an axis here, if I say this is my x-axis, y-axis and z-axis, then it can rotate about this, it can rotate about the y-axis, it can rotate about that, and it can rotate about that also. Okay, so we have an alpha, beta and a gamma, it can rotate about 3 axes. So we have an alpha, beta and a gamma, it can rotate about all the 3 axes. Okay, so sorry, x, y and z axis. Okay, so this is my y-axis and z-axis. So it can rotate about this axis and that axis. So it has 3 degrees of freedom and 3 thetas are there. Okay, so this is called a ball and socket joint. Spherical joint, it has 3 degrees of thetas, and it has 3 thetas, which are the 3 degrees of freedom of the system, of the joint. Now we can attach the links by different kind of joints by using a prismatic joint. If I use a prismatic joint, it can only have a linear translation. Okay. We can have a revolute joint. Now 99%, or if I say 95% robots are made of revolute joints. Okay, and revolute joints having 1 degree of freedom. Okay, now before we proceed further, so what we understand is if we have different kind of joints, we can get different kinds of robot structures. Okay, now if you have a prismatic joint, then essentially you get a translational motion, right? Whereas if you have a revolute joint, you'll be having a rotating motion. So the area inside which the robot can move its end effector would be different, right? And that is basically what we mean by the work volume. So let's now look at the next term, which we need to examine. Is called the work volume. So the work volume is the volume inside which the robot can position its end effector. Okay, and of course the job has to be performed inside the work volume. Okay, now before we go on to that, a little bit discussion is required in terms of the shape of the work volume. We need a little bit more discussion on degrees of freedom. So for example, if I have a table here, okay, we need to understand this before we move on to experiments of robots. So I have a table here. Okay, and on this table I have kept an object. Let's say I've kept my mobile phone like that, flat on the table, and I want to pick up this mobile phone and I want to keep it somewhere. I want to pick it up from here and maybe go like this and keep it there. Okay, how many degrees of freedom are required? Suppose I want a robot to do this. How many degrees of freedom are required? Okay, now if you think a little bit, how do we answer this question? That how many degrees of freedom are required to pick it up from there and take it and place it here? So we answer this question by first assigning an axis. We put an x-axis here. I put an x-axis on this corner, put a y-axis there, and then put a z-axis there. So x, y, and z. Okay, so these are my 3 axes. Now we say that if I want to catch the object, what does catching an object mean? Catching an object means that I want to catch this with a gripper maybe, and I will place my finger like this. This is my gripper. I'll place one finger there, one finger on the other side, and then I'll catch it on the center of the object. Okay, so I'm catching the object. Now to catch the object, basically I need to go to this point, which is xy on that plane. So this object could be anywhere on the plane. So essentially this point could be anywhere on the plane. So essentially it means I need an x and I need a y as a variable. So I need x and I need a y as a variable. After I catch it, I need to move it up. So that's a z, in the z direction. Then I go in this direction. This is also x and y again. Okay, now if this is x and y is already accounted for. Then I can keep it down, that's a minus z. Okay, so there is x, y, and z, 3. Are 3 enough, or do we need any more degrees of freedom? Now, if you think a little bit, this object that we talked about could have any orientation. It could have any, it could be lying at any angle. Okay, so it is like this. Okay, so in this case, the gripper would have to come here now, like this. The gripper will come like this. So what I mean, the gripper angle here and the gripper angle here is different. So I need 1 degree of freedom there to rotate the gripper, because this object could have any orientation on the table. So I need theta also, So there is one more there. So I need 4 degrees of freedom minimum, okay, to catch this object and place it somewhere. Now suppose on the table, let me draw another case. On the table, if I place the object at an angle, let's say there's an angle alpha there on the table, okay, so I'm placing this object with an angle. Now how many degrees of freedom are required? If I use the same logic, what I'll need is I'll need the x, y and z, plus I'll need a rotation at the wrist, plus because I have the gripper will now have an angle like this now. That's my angle alpha. That's my angle alpha now. So the gripper will need one more angle, which is the alpha angle now. So it will become 4 plus 1, 5 degree of freedom. Now suppose the object is having 2 angles. Suppose the object is being is kept such that it has 2 angles. So the object is being kept like this. Okay, there is one angle here and there's one angle there. Do you understand what I'm saying? I hope you understand what I'm saying. In that case, I'll need one more angle, which is beta now. Okay, so if this object is making 3 angles with the surface of that, then I have 3 degrees of freedom there, plus the xyz, which is already here. So you can have 4 degrees of freedom, you can have 5 degrees of freedom, or 6 degrees of freedom. Okay, the minimum is 4 or 5 or 6. 6 is in general, and this is 6. Where did the 6 come from? That 6 came from here. So maximum it can be 6. Normally we require 6 degrees of freedom for a general purpose robot. Okay, you can have more, you can have 7, 8, 9, but general robot would have 6 degrees of freedom. Okay, now please think about this. Okay, now if I were to ask you this question as a homework, please think about it. I will not give you the answer. Suppose on a table, so this is a table. Okay, I keep a cylindrical object. Okay, so I have a cylindrical object. A cylinder I'm keeping on the table. Now I want to pick it up and keep it here. How many degrees of freedom are required? Okay, so how many degrees are required for this task? A cylindrical object, so this is a cylinder, okay, like a water bottle. So how many degrees of freedom are required now? Okay. Now suppose I give you another question. So this is question 1, this is question 2. So another question. Suppose I have a ball. I want to pick up the ball and keep it here now. For a ball. So how many degrees of freedom? Okay, how do you answer that? Well, it will be the same. Put an axis system here, x, y. I mean, the way of solving it is the same, x, y, and z, and then see which motions you require. How do you catch it? And that will give you the total number of degrees of freedom. Please think about it as a homework. It will probably be an assignment question. Okay, now this is a prismatic joint which has 1 degrees of freedom, and it has 1 translating axis. This is a revolute joint which has 1 rotating degree of freedom, which is a rotating axis. Now cylindrical joint has 1 prismatic and 1 rotating degree of freedom. Okay. And this is a ball and socket joint which has 3 degrees of freedom. Now using this various different kinds of joints, we can make different kind of robots. So the first kind of robot is called a Cartesian robot. Now a Cartesian robot essentially has 3 degrees of freedom, and there are 3 prismatic joints, that means 3 translating axes. Now look at the structure of the robot. This is the side view of the robot, and that's the top view of the robot. Okay, now in the side view of the robot, this is the link number 1, this is link number 2, and this is link number 3. Okay, now this link is translating or prismatic, so it means that it can move backward like this, and it can come till here. Okay, so this can go that way backward till there. Okay, and the full axis, this is 1. So basically what you can see, if this is my end effector, this is a straight line like this, it goes back like that. Okay, so this is a straight line. Now that's joint number 1. Joint number 2 is this one. So the full thing can come down. So it can come down like that. Okay, so if it is coming down, what is happening? The straight line is coming down like that. Okay, so if you can imagine that this is my joint, it is coming till here and till here. So the straight line is coming down. So this is a square or a rectangle in the side view. Okay, now if I look at this from the top view, what will you see? This is a planar square or a rectangle. So if you look at this, this is a plane. So from the top view, it will be a straight line, which is this line. This is the straight line. Okay. Now in the top view, the full robot base can move like this. Okay, so this fellow can fully move like this. So this can come till here. Okay, so I hope you understand what I'm drawing. This can fully move this way. Okay, it's the base which can move. So basically this straight line is being dragged all the way like this, and it can come till here. And this is another square or a rectangle. So if I add this and this in the side view and the top view, what is the shape you'll get of the work volume? It will be a rectangle. It will be a cuboid. Okay, so it will be a cuboid like this, or a cube. Okay, if all the lengths are equal, it's a cube. If the lengths are unequal, then it's a cuboid. Now this end effector of the robot can go every point inside the cube or the cuboid. It cannot go outside. So the shape of the work volume of this cylindrical, of this Cartesian robot, is a cube or a cuboid. Okay, you should draw it by yourself and try and understand. So it's very, very simple, and the procedure is the same for all drawing work volume of all the robots. So first thing that you do is that you take it from here to here. So this is the first joint which can go from here to here. So this can go back like that. Okay, so from here till there, and after it goes back till there, it is basically a straight line which it is carving out in space. And then this full joint, this joint number 2, it can come down like that. So this full thing can come down like this till here. Once it comes down, what is happening? This straight line is coming down like that. So what shape do you get? You get the shape of a square or a rectangle. Okay. Now in the top view, if I look at this planar square or rectangle, I see a line. So this is my line. Okay. And then what we can see is this base can fully move like that. Okay. So the base can move, so which essentially means this is moving like this, and this is another square or a rectangle. So if I join this plus this, what will we get? We get the shape of a square, we get the shape of a cuboid or a cube, and every point inside there the robot can go, every point outside it cannot go. Okay. Now let's look at a cylindrical robot. A cylindrical robot has 2 prismatic joints and 1 revolute joint. Okay. Now the 2 prismatic joints are shown in the side view, and the revolute joint is shown on the top view. So the prismatic joint side view and that of the Cartesian robot is exactly the same. So there is one joint which can move this much. It's a prismatic joint, so it can just translate like this. So what you get is a straight line. Then you move this down, so this full thing can come down like this, and the straight line has come down like this. Okay. So the straight line has come down, and what do you get? You get a square or a rectangle. Now if you look at the top view of this square or rectangle, what you see is a straight line like that. Okay. Now in the top view, which is the revolute axis, this is the revolute axis which is pointing upward like that. Okay. This is, so on, from the top view it will look like a point. This can rotate about this axis. So this line can rotate this way, or it can go this way. Okay. So when it is going till here, so this line is going like that. Okay. It is rotating. Okay. So what is happening is, on the top view you're getting a circle, a big circle here, and then a small circle inside. Okay. Now if I add this one plus this one, what will be the shape? It will be a hollow cylinder. It will be something like that. Okay. So it will be a hollow cylinder. Now every point inside the hollow cylinder the robot can go. Anywhere outside the point the robot cannot go. Okay. So what you see is that the shape of the work volume for a cylindrical robot and that of a Cartesian robot are different. Okay. In this case it's a cube or a cuboid. Here it's a hollow cylinder. Now let's look at the case of a 2 degree of freedom planar arm. Okay. Before we go on to a articulated robot having higher degrees of freedom. So let's look at how do we draw the case of the work area or the work volume of a 2 degree of freedom planar arm. Now let me say that this has 2 degrees of freedom. It is planar. It has 2 R joints. So it is this is one link. Let me change the color and draw another link. This is the second link. Okay. So it has one axis here, another axis. The axis is coming out of the board. Now let's say theta 1 and theta 2 can move 0 to 180 degrees. Okay, let me say it moves 0 to 180 degrees. Okay. So how do we start drawing it? Number 1 is theta 1. This is my theta 1 and this is my theta 2. So first thing that I do is I'm going to move my theta 2 from 0 to 180 degrees. So this will come and bend like that. Okay, that has become, so first I move theta 2. Then what I do is I move theta 1. Then I move theta 1. 0 to 180 degrees. Just for the sake of explaining this, I'm saying it is moving 0 to 180. So this one is rotating now. So what is happening? This one is coming like this, and it has become on this side now. Okay. Okay, so this will come like this till here. Okay, that's my theta 2. Okay, so I have drawn theta 1 going from 0 to 180 and theta 2 going from 0 to 180. What I get is one circle, another circle, two circles. Now let me go back to the third one again and say that if both of them are fully stretched like this in the initial condition, okay, this is my, so if I say they are fully stretched, this was my base. So when it is fully stretched, it was here. Okay, so third is I'm going to move fully stretched. Okay, and I'm going to move theta 1 from 0 to 180 degrees. Okay, so what will happen is this outer fellow will go like that. Okay, now if I open it, what will happen? This will come back like this. Okay, this is my, okay. So now what we are seeing is that there is two circles in the inside and one circle on the outside. And when I open it, there is one circle here. Okay, let me explain this again. Let me draw it again to make it clearer. So there is 2 degrees of freedom. This is the base, which is not moving. This is one link. And there is another link there. Okay, there's the second link. Okay, that's the second link. So the first thing that I do is I move this. So this is my theta 1, that's my theta 2. So I move this here, it comes this side. I move theta 2, it comes here. Then I move theta 1. I move theta 1, I rotate theta 1, I come till here like this. Okay. Then what I do is I keep both of them stretched in the initial condition and I move theta 1, I get one big circle like that. Okay. So this one is equal to, if my L is L1, this is L2, then it's L1 plus L2. Okay. And after coming here, I can open it like this on the back side. It'll come like this. So this one is always L1 plus L2. And the small fellow is always L1 minus L2. Okay. So basically on the second side, on the inside, we have two circles. On inside, we have two circles. On the outside, we have one circle. Okay. Now, suppose I had 3 degrees of freedom. Let me extend the logic to 3 degree of freedom system. There's one here, and one here now. This is a 3 degree of freedom system now. 3 are planar. Okay. Now, if I draw the same thing, I get one like this. Okay, this has come like this. Then this fellow has come here, and then that fellow has gone there. Okay, so I'm getting 3 circles, 1, 2, and 3. On the outside, it's always one circle. Okay, outside is always 1, inside is 3 if there are 3 degrees of freedom. If it's 2 degrees of freedom, there are 2. Okay, so on the inside, you'll always have 2 degrees of freedom. Outside, always you have 3 degrees. You have always one circle. Inside, you can have 2 circles, 3 circles, depending on how many degrees of freedom are there on the system. Here again, you should please draw this by yourself. Okay, once you draw it by yourself, it becomes very clear. Okay, what the shape is like. Because we need to draw this for large degree of freedom manipulators. So you need to understand how this happens very clearly. Now, an articulated robot has 4 degrees of freedom. It has 4R joints, okay, 4 revolute joints. And 3 of them are planar. This is the side view. So there are 3 joints, one here, and one here. So this is like this, okay. So this is very similar to the one I drew here. So it is equivalent to this one. Okay, there is one joint here, one joint here, and one joint there on the plane. So it is like this. So when I draw it on the degrees of, if I draw the work volume, what will it be like? First, I'm going to move this one. Then I move this one, second one, then I move the third one. So there are three out there. Okay. So we said that if there are 3 degrees of freedom, then there'll be 3 circles in there. So there is one here, another one there. So there are 3. On the outside, it's always 1, which is one circle, L1 plus L2 plus L3, whatever it is there. Now, if I look at this from the top view, this is planar, right? This is a planar shape, but it's on a plane. So if I look from the top view, what I'll see is a straight line here. Okay, it will be irrespective of the shape. So on the top view, when I rotate this one, what will happen is this straight line will start moving like that. Okay, the straight line is moving. And when the straight line is moving, what we get is again a hollow cylinder. We get 2 circles, one circle here, one circle there. So if I combine this one and this one now, what will be the shape? Now the shape is going to be a sphere. It will be spherical, and there will be some small parts cut inside in between, but it is spherical in shape, so it's spherical, right? So it's a sphere similar to a human. For the human arm also, our work volume is more or less spherical, and inside there are some parts which are cut out. These cut out parts correspond to these parts. Okay, so this is how we draw the work volume of different kind of robots. There is another robot which is very commonly used, called the SCARA robot. So the SCARA robot is very commonly used in assembly applications. So this is called the selective assembly. So this is called selective compliance assembly robot arm. Okay, which means that this robot has 4 degrees of freedom, and it has 3 revolute joints and 1 prismatic joint. Okay, now let us say this has 3. So this is the side view. This is 1 revolute joint. There is 1 revolute joint at the wrist. There is 1 revolute joint here. Sorry, the revolute joint is at the wrist here. 1 revolute joint there, 1 revolute joint here, 1 revolute joint here, and this joint is a prismatic joint, which is D joint or a prismatic joint. Okay, so this is my theta 1, this is my theta 2, that's D3, and that's my theta 4. Now this is the side view. Now if I see the top view, then the top view is shown here. So in the top view, this is like a planar 2-link arm. Okay, this is 1 link here, another link here. So this can rotate. So when it is fully stretched, you get 1 big circle. When this fellow rotates backwards, it comes like that till here, and then rotates, you get a small circle here. Okay, so it is here on the top view, you're getting 2 circles. Okay, and on the side view, if you look at it from this side, this can go up and down. This is a prismatic joint which can go up and down, so it's a straight line. Okay, so the straight line can be rotated about this axis and this axis. So what you see is actually a part of a cylinder. Okay, so if you can imagine on the top view, this straight line can move like this and like this because of this axis and this axis. So if you're looking at a cylinder from the side, this is also a hollow cylinder. Okay, so this is also a hollow cylinder here. Okay, so this is a hollow cylinder, and this is the work volume of that of a SCARA robot. Okay, now some interesting questions that we need to answer here. We saw that a robot can be made up of different kind of links and different kind of joints. The links can have different kind of shapes and different shapes and sizes that we'll see as we go along. How do you assign your DH parameters there? And it can have different kind of joints. So with different kind of joints, you can get different kind of robots. Okay. Now we also looked at how many degrees of freedom are required, and we said that the minimum is 4. Now we need to answer this next question. That is, what should be the link length of the robot? Okay, we said that for a robot to pick up an object and keep it at any at some angle, it needs minimum of 4 degrees of freedom. But if you want to keep the object at an angle, you may need 5, or you may need 6, or you may need higher degrees of freedom also. But what about the link lengths? Okay, so now let's try and answer this question: what should be the link lengths of a robot? And we can answer it very simply from here. Exactly what we have done so far is we looked at a 2 degree of freedom robot arm. This is one link, and there's another link there. Okay, so this is my theta 1, this is my theta 2. Now let us say that theta 1 and theta 2 can move from 0 to 360 degrees. Okay, in the previous case we had limited it to 180 degrees, but now let's say that we remove the limitation and we say that it can rotate full 360 degrees. Okay, so now this fellow can go 360, means it can go down like this, it can come till here, full like that. And that is theta 2. Theta 1 can rotate fully and it becomes a circle, full big circle like that. Okay. Now this can go till here, in the reverse direction it is there. That means it cannot go here. So if I were to draw this circle, it can go here, but it cannot go to these points. And then if I draw, what I'll get is a circle here. Okay. So it's like saying I'm getting this circle. Let me draw it again and explain what I just did. This is 1 degree of freedom. This is the 2 degrees of freedom, planar. It can go 0 to 360 degrees. Both the joints can rotate that much. So this can rotate 360 degrees, so it becomes like that. Then this one can rotate 360 degrees. So it's like saying that this one can rotate 360 degrees, means it can get a big circle like that. And for every thing here, this fellow is this circle is also moving. So this circle is also moving. Okay, so this is generating another circle there. I hope you can understand what I'm saying. Okay. So what we get is a big circle and a small circle. Now in this small circle, the robot cannot go inside there. It cannot go in there. Why? Because it is limited to only this much. Okay. So it can only go this much till here, right? So it cannot come this side now. Sorry. From here till here. So that is like this. So it cannot come here. So this circle is there. This circle is getting swept around like that when theta 1 is moving fully. So what you are getting is different circles like this. And the base of the circle is drawing out another circle here. And the robot cannot go inside there now. Okay. Now we are asking the question. That in this 2 degree of freedom system, this is 1 degree of freedom and there is another degree of freedom here. That's my 2 degree of freedom system. Okay. What should be the ratio of L1 to L2? Suppose it is A. Then what should be A? Okay. What should be the ratio of L1 to L2? Now, how do we answer that question? We know that the shape of the work volume is like this. This is 1 and this fellow comes like this here. So there is another circle there. Okay. This is the shape of the work volume, or the work area in this case, because it's planar. So now if I want to say what should be A, then one way is that it should have maximum area. It should have maximum area. Okay. Now it cannot go inside there. It can go inside there only, the end effector, right? So it should have maximum area. Now what is the area? If this is my V1 and this is my V2, then the area V is equal to V1 minus V2. Okay. And now if you say that V is equal to pi, what is the total outside? L1 plus L2? L1 plus L2 squared minus pi into L1 minus L2 squared. Okay. That is the area where, that is this area. Now if I want to maximize that, what should be A? One way of solving the problem is that you have two variables here, L1 and L2. So convert it to one variable. So say that L1 is equal to A times L2. So wherever there is L1, you put A times L2. So this equation will only have L2. And then you do dV by dL2 equal to 0. And for different values of A, see how this changes. That's one way of solving it. The other way of solving it is geometrically. Just by looking at the figure, can we say that what will be the ratio of L1 to L2? Now, if L1 is bigger, if L1, L2, this area that it cannot go into, okay, is decided by L1 minus L2, right? This is L1, that is L2. So this area is decided by L1 minus L2. So this part is L1 minus L2. Let me draw it again. Yeah. So this small fellow here, this depends on L1 minus L2. The outer fellow depends on L1 plus L2. Now, whatever is the ratio of A, L1 and L1 plus L2 will always be constant, irrespective of the ratio of A, because the outer circle will be fixed because it depends on L1 plus L2. Okay. Whereas the inner circle depends on L1 minus L2. Okay. That depends on A now. Okay. So whatever is the value of A, this circle is constant. This fellow will not change, whereas the smaller one will change. Now, if you want to maximize the area, which is equal to the outer circle minus the inner circle, then if the inner circle is equal to 0, then the area is maximized geometrically. And this will become 0. V1 will become equal to 0 when L1 minus L2 is equal to 0, which means L1 is equal to L2. What does that mean? That essentially means that if both the lengths are same, this is one and this is the other one. Okay. If both the lengths are same, what is happening when it's turning? This fellow is coming here. This is the point now. So this inner circle is shrinking to a point and is becoming a point there now. Okay, so in that case, what is happening is that your point, this is becoming a point, this circle is becoming a point, and L2 is 0 now. So now you have maximum of V1 because your full volume has equal to V1 now. And that condition is only when L1 is equal to L2 or L1 by L2 is equal to 1. That means A is equal to 1. So in all robots, you will please note this link lengths are equal. Okay, if link lengths are not equal, then the robot, then what will happen is there will be a region inside the robot where the robot end effector cannot go. Okay, so this is something that is very important to remember when we are talking about when we talk about design. When we look at actual experimental robotics, we'll see that the work volume, the link lengths are always equal. Look at industrial robots also. You will always see that so even when you look at industrial robots, you'll always find that the link lengths are always equal. Okay, so whatever robots you see, the link lengths are equal, and that is the reason why. Otherwise, you'll end up with a region inside where the end effector cannot go. We talk about this region as being the singular region, and as we go along, we'll look at things like singularities and discuss in other classes. So today we looked at the basic definition of intelligence, although that is not the objective of this course. But we essentially said that a machine may be called intelligent if it has some attribute like human, like intelligent ability. Okay, and there is a Turing test which is actually designed to check if machines are intelligent. After that, we looked at different kind of joints, how many degrees of freedom the joints have, and by making using different kind of joints, we can make different kind of robots. And we also saw that the work volume of the robots would be different for different kind of joint based structures. Okay, now out of all those robots, the strongest robot is the Cartesian robot. Okay, and the human arm is similar to the articulated arm. So as a homework, you can try drawing the work volume of the human arm. So your arm has how many degrees of freedom? You can think about it. And then what is the shape of the work volume of the human arm? Okay, please think about it. Maybe in the next class we'll discuss that. Okay, so we stop today. Thank you.